Good afternoon, everyone. A very warm welcome to all the respected dignitaries who are present here, and beloved teachers and our enthusiastic students. Today, we are here for the special lecture series on convergence and probability, exploring limits and random walk by Aladi Sitaraman sir, who happens to be the retired professor from reputed institute, Statistical Institute, like, and Professor B.V. Rao, who also retired from the esteemed Chennai Mathematical Institute. And we really thank for the Department of Mathematics and Department of Physics for organizing such a wonderful seminar. Now I request our beloved student Satya to deliver the welcome address.
Good afternoon, everyone. With immense pleasure and great pride, I extend a warm and heartfelt welcome to everyone gathered here for the inaugural session of the 3-day lecture series organized by the Department of Mathematics, BMS College for Women, for the students of BSc and MSc Mathematics. It is an honor to acknowledge our esteemed Chief Patron, Dr. B.S. Ragini Narayan, Donor Trustee, Member Secretary, BMS ET, and Chairperson of BMS College for Women in her absentia, whose visionary leadership and unwavering encouragement continue to inspire our institution. We are also honored to best wishes conveyed for this program by Dr. Dayanand Pai P, Life Trustee, BMS ET, Shri Aviram Sharma, Trustee, BMS ET, and Wing Commander R.A. Raghavan, Director, BMS ET. A warm and respectful welcome to our beloved principal, Dr. Raghu Kumara N, whose commitment to academic excellence and quality education continues to guide our institution towards greater heights. I also extend a cordial welcome to our Dean Academics, Dr. Bhuvaneshwari E, for her continuous support and guidance in all the programs. I also extend a cordial welcome to IPSC Coordinator, Dr. Shubha Ma'am. I also extend a cordial welcome to Controller of Examination, Dr. Vaishali Ma'am, in her absentia. I also extend a cordial welcome to Head of the Department, faculty members, and dear students. Your presence, your presence make this academic gathering a truly meaningful. Today, we are immensely privileged to have with us two eminent mathematicians whose contributions have enriched the field of mathematics across the world. It is now my great honor to introduce our first distinguished speaker, Professor Aladi Sitaraman. Professor Aladi Sitaraman is one of the India's most celebrated mathematicians and internationally acclaimed scholar in harmonic analysis, Fourier analysis, Lie groups, representation theory, and mathematical analysis. Professor Sitaraman completed his BSc from Osmania University, earned his BA honors from the University of Cambridge, United Kingdom. And obtained his PhD in mathematics from the University of Washington, USA in 1975. He began his distinguished academic career at the Indian Statistical Institution, where he served as associate professor in charge of the division of theoretical statistics and mathematics, and head of the statistics and mathematics unit at the ISI Bangalore Center. Today, he continues to serve the mathematical community as Emeritus Professor at the Indian Statistical Institute, Bengaluru. Professor Sitaram has held prestigious visiting appointments at the leading universities, including University of California, University of Washington, University of New South Wales, University of Melbourne, Australian National University, University of Sydney, and the University of Western Australia. He has delivered advanced lecture courses across India and has played a significant role in organizing several summer and winter schools through ISI, TIFR, and MBHM. His pioneering research in Fourier analysis, harmonic analysis, life groups, symmetric spaces, integral geometry, representation theory, and mathematical uncertainty principles has earned international recognition. His publications have appeared in many of the world leading mathematical journals, and his books our first course on representation theory and linear light groups mathematical analysis continues to guide students and researchers worldwide. Professor Sitaram was elected Fellow of the Indian Academy of Science in 1991. He has served on its council, contributed to national science education initiatives, edited prestigious mathematical journals, supervised numerous doctoral scholars, and served on the several academic and research committees of premier institutions. It is indeed a matter of great pride for all of us to have among us a mathematician who research excellence and dedication to teaching have inspired generation of mathematics. On behalf of BMS College for Women, I extend a warm and heartfelt welcome to Professor Aladi Sitaram. Sir, we deeply honor you, your gracious presence, and eagerly looking forward to your enlightening lecture. Thank you.
Thank you, Satya, for such a wonderful welcome speech. Now I call upon Cynthia for the introduction about eminent Professor B.V. Rao, sir.
Good afternoon, everyone. It is a great honor and privilege to introduce our distinguished speaker, Professor B.V. Rao sir, an eminent mathematician, outstanding educator, and one of India's foremost experts in probability theory, measure theory, stochastic processes, and mathematical analysis. Professor B.V. Rao sir began his academic journey by earning his master's degree in statistics from Osmania University in 1965. He later obtained his PhD from the Indian Statistical Institute ISI, Kolkata, in 1970, laying the foundation for an extraordinary career in mathematics and statistics. For more than 3 decades, Professor Rao sir served with great distinction in the Division of Theoretical Statistics and Mathematics at the Indian Statistical Institute, where he made significant contributions to teaching, research, and academic leadership. Following his retirement as Distinguished Professor in 2009, he continued his academic pursuits as an adjunct and visiting professor at the Chennai Mathematical Institute, where he remains an inspiring mentor to students and young researchers. Professor Rao Sir's research spans several fundamental areas of modern mathematics, including probability theory, stochastic processes, descriptive set theory, measure theory, and mathematical statistics. His work has advanced our understanding of the mathematical foundations of randomness and has had a lasting impact on research in probability and analysis. An exceptional teacher and author, Professor Rao has co authored several influential books. Among them, Measure Theory for Analysis and Probability has become an important reference for graduate students and researchers successfully bridging the disciplines of mathematical analysis and probability theory. His earlier work on Borel spaces is also regarded as a significant contribution to advanced mathematical literature. Throughout his illustrious career, Professor Rao sir has been widely admired not only for his research excellence but also for his extraordinary dedication to teaching and mentoring. He has guided generations of students, inspired countless young mathematicians, and played a vital role in strengthening mathematics education in India through the Indian Statistical Institute, the National Board for Higher Mathematics, and the Chennai Mathematical Institute. His remarkable contributions have been celebrated by the mathematical community through prestigious events such as Conference in Analysis and Probability, organized by the ISI Delhi Center on the occasion of his 70th birthday, and the CMI Colloquium commemorating his 80th birthday, reflecting the immense respect he commands among mathematicians across the world. Today, we are indeed fortunate to have with us a scholar whose life has been devoted to advancing mathematics through outstanding research, exceptional teaching, and unwavering commitment to academic excellence. On behalf of the Department of Mathematics, BMS College for Women Autonomous, I extend a warm and heartfelt welcome to Professor B.V. Rao, sir. Sir, it is a privilege to have you with us, and we eagerly look forward to your enlightening lecture on random walk. Ladies and gentlemen, please join me in extending a warm round of applause to welcome Professor B.V. Rao, sir.
Thank you, Cynthia, for a great introduction. Now, I would like to welcome Rajsekhar sir for this session. Now, without further delay, I would like to request Dr. Professor Aladi Sitaramam sir to begin the session.
Switched on or can you hear me? Is there a lot of echo? No? Fine? Okay. First of all, I'd like to thank you all for being here and listening to a couple of professors, very old, but but I hope you will get something from it. Professor B.V. Rao is senior to me both in ISI as a professor as well as in years. So I have great respect for Professor B.V. Rao, and I was happy that I could persuade him to come here. We meet as old friends who have known. Okay. Yeah. As old friends who have known each other for 50 years, that is for you a very long time, because I think most of you are Gen Z people, and so this must be prehistoric, you know. So, yeah. Okay. Is it okay? Okay. Yeah. Is it okay? I don't know where I was. Yeah.
You can continue.
Uh, so, first of all, it's a pleasure to thank various people who have organized these lectures. Dr. Raghu Kumar, who is the principal of this college, and uh, various others. I'm afraid my memory is very poor in non-mathematical things. But I would like to thank the HOD of Mathematics degree program, that this Vijay Lakshmi Shanba. That's right. Hi. They have come to see me at my house, so I'm very grateful for your presence there. And Dr. Bhuneshwari, HOD of Mathematics of the PG program, and uh, this Dean Academic Affairs, Dr. Bhuvaneshwari, and and if I don't name the other people, it doesn't mean I'm less grateful to them. I'm equally grateful to all of them, but I don't want to keep repeating names. They're all here. They're all your teachers, and I'm sure. And I also should thank the physics department, which is represented by uh, um, I do know his name, but Pramod Kumar. Yeah, yeah, so Pramod Kumar. And originally, when we all met first in my house, I told them that there will be 3 lectures on mathematics and 3 on physics. Okay, but and then after a lot of thinking, I thought it would be good for you to listen to some 3 lectures on probability theory, especially something like random walks, because although strictly speaking it's a different subject, it is part of physics also, and part of many other disciplines like economics, various other things. So I would say that I have partly fulfilled my promise of getting somebody to give 3 lectures on physics. But if you would uh, modify the definition of physics to include probability theory, which it is, statistical mechanics, large parts of ergodic theory, various things like that are part of physics, and he's an expert on many of those areas. So, and I consider him more a teacher because when I joined as a young faculty member in ISI, Calcutta, he was already several years, he has been there as a professor. And I was a.
Can you connect your tab?
Huh?
Can you connect your tab? Tab connection.
Okay, yeah. 1 minute. I have to. Okay. I so I owe a lot to him in terms of my early years in Calcutta. As I said, we have known each other for 50 years, and so we called him a holy terror in those days because if he was in the audience, we would be very scared that he would find fault with some of our mathematical arguments. So I used to prepare specially carefully when he was around, and I have done that today also because he is there. I dare not make a false statement. Okay, so so I will just start. And if I've left out the names of some of the people who have organized, please accept my apologies so that we can move on with the lecture. Okay, uh, is that coming? I'll tell you what I want. No, 1 minute. Okay. How do I go to my page? Okay. It's not. 1 minute.
Okay.
Is it coming? Is coming? Can you see that on the board, or is it okay? Can you see it on the board? What appeared here? Okay. So let me start by saying that my lectures, these three lectures, will be somewhat informal, somewhat non-rigorous, somewhat, what do you call it? Uh, Not very thorough. Just give you an idea of some of the things that we encounter in mathematics. Okay. Uh, uh, See, the notion of a sequence may seem very specialized, but it is central to mathematics, mathematical analysis. Okay. Can you read it? Huh? Okay. Can you read what's on there? Okay. Anyway, so it's my development will not be systematic and will not be very rigorous. The rigor and the systematization of what I am doing is the job of your BSc teachers. So I'm not here to replace what your BSc teachers are going to say, but only to give you an idea on the various approaches that we have. Some of it you may have seen already. So first, before I start, I want to know who are all the BSc first year students here? And the others are more senior students, or BSc, are there any MSc students? Second year? Um, Second and third year. So especially for the second and third years, some of what I'm saying must be very, they might know that already. And so I hope you will bear with me because I'll be repeating something that you know. Okay? So let me first start with the notion of a sequence. Okay, what is a sequence? A sequence is just a listing of some numbers, real numbers. I hope you know what a real number is. You think of it as an infinite string with some point marked as zero, and things to the left I will call negative, things to the right I will call positive, and the distance from zero along the string is a real number. Okay. For instance, it could be 384 or it could be 79 by 42. Okay. So it can be anything. Rational, irrational. Some of you would have heard of irrational, rational, irrational, all kinds. So I'm not going to define these terms carefully because in three lectures, how can you define everything carefully and so on? What I take for an entire semester to cover, I'm trying to give you an idea in three lectures. So obviously, I'm not going to be able to cover much, only just some idea. Okay. So the concept of sequences is central to analysis. And and why is it central to analysis? Let us look at some special examples to convince you that the concept of sequence is essential. So let me move to the very easiest example, geometric series. You would have all heard of this. I called it series, but I'm going to manufacture a sequence. Given a positive number A, let's say it's positive. Let's given a positive number A, let us look at the following series Gn equal to, for each n, look at the sequence. Gn equal to 1 plus a squared and so on plus a to the n. Okay. So now, what do we know about this series? As n gets larger and larger, does this series approach any particular number? If so, what is that number? Can someone tell me what the number is? You know the formula for the sum 1 plus a squared and so on up to a to the n. Can you tell me at least what that formula is? the famous sum of the first and
Natural numbers.
no need to memorize. Okay, I don't memorize it. So take 1 plus a up to a to the n, call it s, sn or s, and multiply on the left by a, then it becomes as. Then you will get a plus a squared to a plus n, or a to the n plus 1. Shift that a little so that the powers come one below the other. Subtract. And then you will find that, subtract the first from the second. So you will find that uh, a times Sn plus 1 minus Sn is equal to something. Solve that for, I'm sorry, a times Sn minus Sn is something. So solve that for Sn. So you get a formula for Sn. Quickly do that on your notebook and let me know what you get. So what is Sn? I mean, it takes 2 minutes. I'm sure you are all faster in doing that kind of calculation than I am. I'm a very old man and you are all young people at your age. You should be able to do that. This is not going to be a lecture where I say something and you all listen and copy down. This is going to be more an interactive lecture. And if you don't do that, then we won't proceed very much, I'm afraid. So tell me, somebody here, you don't have to stand. Yeah, okay. Anybody, not the teachers, anybody here who is done? Yeah.
A into 1 minus r power n.
Yeah, but you are one of the teachers. I want one of the students to answer me. Yeah.
R is what? Ratio is what?
Can you, do you have a mic?
Mic, yeah,
and
I'll
mics which you can
Yeah.
tell me? I can't hear properly. If you can't hear, if you can't get up, if you can't write, you might ask, why is he here? But I hope you will get something from my lecture, so. You can sit down and speak. All I need is to hear, I don't have to. Okay, you can come and tell me here and I will shout it out. Yeah.
A into r power n minus 1. R is the ratio
A to the power.
A into r to the power n minus 1.
What is R? I didn't write down.
Ratio.
I only wrote 2 things here. A squared up to a to the n, and I have written Gn here. Gn is the sum up to 1 plus a squared up to a to the n. So your answer must involve what I have written down, right? I have not introduced any R, right?
The difference between first term and second term.
Between?
First term and second term.
Is it difference or multiplication?
Divide, multiplication.
So if you multiply 1, you get a. A times 1 is a, right? No, I don't want to embarrass you. Please. Not, it doesn't matter, Even I am very self-conscious in front of all of you and I feel self-conscious. So I ate something quickly at home and my wife said this will calm you down. So I've taken that and come here. So don't bother. Take it easy, take it, even if you can't answer, it doesn't matter. Somebody else will ask, that's all. So don't worry about it just because. Don't think I am bullying you, No bullying involved, no ragging, nothing involved here. Anybody who can, tell me, it doesn't matter, you tell me. Whoever knows can tell me, it doesn't matter, yeah. Or show it to me if you have written and you don't want, right?
So a into 1 minus a power n divided by 1 minus a.
Right. So what she told me was, it is a times 1 minus a divided by 1 minus a power n. Right? 1 minus a, sorry. A divided by 1 minus a times that numerator is 1 minus a power n. Okay. Uh, Now what happens as n gets larger and larger? You tell me. Suppose you have to break up into two cases, right? What are the cases? Please sit down. You know, don't have to stand there. Right? And also, anybody who wants to answer can sit and answer me, or bring the notebook and answer me here. Okay? Tell me. I mean, we can't proceed unless we resolve the simplest case. A squared, a cube. Supposing a is 10, what happens? Powers of 10. 10, 10 squared, 10 cubed, 10 to the fourth. What happens to that? Is it getting closer to some area or some quantity, or is it getting larger and larger? So this sum, Gn, to use a expression that we always use informally in mathematics, it blows up. Doesn't get to any, it gets larger and larger. Remember, see that it is the formula you gave me is positive, right? Because 1 minus a to the n divided by 1 minus a. If a is larger than 1, then the numerator is negative, denominator is negative. So I can write it as a to the n minus 1 divided by a minus 1. Is that okay? By taking out a negative. So as a gets larger and larger, I'll get the bottom, the denominator becomes 9 because 10 minus 1 is 9. And the numerator becomes 10 squared minus 1, 10 cubed minus 1, 10 to the fourth minus 1. It's not going to stop. So that means that it goes up. And one way of expressing it is it goes to infinity. It's just a way of it. It's a language. So it goes to infinity. So you have a sequence which goes to infinity. The case when a is 1 is very trivial because you have 1 plus 1 plus 1 plus 1, and you can all see that that also cannot be bounded by anything because some 1 up to n terms will get n. Then as n gets larger and larger, it gets larger and larger. So obviously there is no limit. It again goes to infinity. Okay. We are only dealing with positive terms. To make it simple, I am giving you only positive terms. Right? Is that okay? Okay. So now what happens if a is less than 1? So look at that formula. 1 minus a power n in the numerator divided by 1 minus a. What happens to that?
The number gets smaller and smaller.
Yes?
So the number gets smaller and smaller as you raise the
Correct. Eventually it will be so negligible. So approximately what will be the size? It will be, it started with 1. It will be 1 over 1 divided by 1 minus a, right? So if you take, for instance, half and you write it and you ask what is 1 plus half squared plus half cube, what is it add up to? I mean, you know, roughly, intuitively I'm asking. So you will get 1 over 1 minus half. So that means 2, right? 1 minus half is half. 1 divided by half is 2. So the sum of the series 1 plus half cube, or in other words, the sequence which we build out of the series by taking the partial sum up to n terms, right? That gets closer and closer to 2. And it will always be less than 2 because I have taken only positive term. So every time I get something, I get closer to 2, but not quite to 2. As n gets larger, it is getting larger. So you express this by saying that the limit of Gn, which I have written down there as the sum, that is equal to a. Sorry, 1 minus a. If it begins with 1, it is 1 over 1 minus a. If it begins with a, it is a over 1 minus a. I don't know what I have written. I can check. 1 plus a I have written. So it is 1 divided by 1 minus a. If that is the common ratio, it is called by. So one of the earliest examples of sequences was manufactured out of something which came from a common ratio, right? It's a common ratio, right? A divided by 1 is A square divided by A is A. So the simplest possible series is 1 plus A plus A squared and so on, okay? That's, we can now pass on, right? I mean, we have understood geometric series. The simplest of the series is geometric series. I don't think in BSc final year or second year you will ever be asked a question about geometric series. So what I said may not be important from the point of view of exam, but it doesn't matter. It tells you about size of things and so on. Okay. So the next one, I want to ask you this question. Many of you or your parents may have started a fixed deposit. Huh? Supposing I give you 1 rupee and I say that I will give you 100% interest on 1 rupee, 100% a year. Then at the end of 1 year, how much do you have? 100% I'm giving you. Very generous. I'm a very generous man. So, yeah.
2 rupees.
2 rupees, right? Okay. Supposing instead of just doing simple interest, I compound it twice. One, then again in the middle of the year, and then again, how much will that be? Don't look at formula. Just tell me, calculate it in your mind. Tell me.
4 rupees. 4.
Yeah. 1 plus half whole quantity squared, right? So, this quantity will be a little larger than 2. Otherwise, there's no point in doing compound interest, right? So I'm not giving you a rigorous proof, but I'm just saying from common sense, if I compound interest twice a year, then it is more advantageous than once a year. What happens if I do it 3 times? That is every 4 months. 4 months, right? 4 months, 4 months, 4 months. Then what will be the final amount you get? Yeah, same logic. 1 plus 1 by 3 to the power of 3. It's written there, I think. Yeah. So 4 times 1 plus 1 over 4 to the power 4. In general, if I do it n times, I will get 1 plus 1 over n to the power n. Okay. Now, I'm saying that if you make n larger and larger and larger, 365 times, that means every day. Make it even more, every minute of the day, every hour of the day, then make it every minute of the day. Okay? Huh? That is what they call cumulative. Make it cumulative. How much will you get at the end of the year? That means I'm asking you the following mathematical question. What is 1 plus 1 over n to the power of n as n gets larger and larger? Does it come closer and closer to a particular number? That's what I'm asking you, right? Anybody here who would like to answer? If it's wrong, doesn't matter. I give hundreds of wrong answers. You ask Professor B.V. Roy, phone him up and say, will you please tell me if this argument is correct? And very often he says, it's rubbish. You know, he's a very polite man. You won't say rubbish, but he will dismiss that argument. Tell me the correct argument. So no problem about giving wrong argument. No, don't worry about it. Yeah.
But it tends to the close to the value of E, which is 2.7.
Roughly 2.7 or exactly 2.7?
I think roughly, sir.
Roughly. Okay. What
Very
is that?
close to that, possibly.
What do you get? What is that number called? You would have come across that number, right?
2.7.
No. That is a symbol for a very famous symbol for
E.
E, right?
Yes.
Okay. So that number is called E, and she said, which is correct, that it's approximately 2.7 then to You can make it better, better approximation. 732, is it? 732, etc., etc. So this 1 plus 1 over n to the power n, surprisingly, as n goes to infinity, if you just look at it, you might say, oh, 1 over n goes to 0, right? 1 is there. 1 to the power n, we know for any n, 1 to the power n is 1. So intuition sometimes can be wrong. So you have to check a few cases. Then you see whether you can get a general pattern, and you can prove that 1 plus 1 over n to the power n goes to something which is between 2 and 3. You can prove that by using the binomial theorem. And then by using binomial theorem again, you can show that it is an increasing sequence as n goes higher and higher. But I use the common sense argument, namely, if you compound it 100 times and if you compound it 200 times, obviously compounding it 200 times will fetch you more, right? So you have to use your intuition, and then you have to use logic and mathematical argument to make it precise. That's the way the game is played. Uh, the game, I'm not saying it's not serious. It is serious, but that is the way the game is played. Okay. First, use intuition, get an idea of what is working, and so on. Okay. So that is. Then I've written something here which is about another sequence which I've written as capital En, and that sequence is 1 plus 1 plus 1 over 2 factorial plus 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 up to 1 over n factorial. Is that visible there?
Yes, sir.
Okay. So if n is 0, we interpret 0 factorial as 1. 1 factorial is 1. So if you want to write a pattern, to see the pattern, you write it as 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial and so on, up to 1 over n factorial. This sum you call capital En. Question: will this go to some limit? Will En go? Will increasing, right? You are adding another positive term for En plus 1. So En plus 1 will be greater than En. So on, it's increasing. Will it blow up? To use a language I used earlier, blowing up. Or will it go towards, it will go up and up, but it will come to a particular quantity. Do you think it will come to a particular quantity? Yeah? Yes, if you are not able to quickly come up, it doesn't matter. Yes, what do you think? Do you think it will
could tend to a
become
finite value. Sir, it could tend to a finite value because as the as n increases, the denominator increases, so the number reduces in
Okay.
value. So
I'll come to the reasoning, because that reasoning which you gave me is not quite right, because I'll give you an example where each number will become smaller and smaller and go to 0, but still the whole thing doesn't come to a finite point. We'll come to that. But your conclusion is right. En goes higher and higher and it approaches. Let us call that quantity capital E. The question comes, is this E, small e and capital E the same thing? That is the big question. No? No? Some people say no. Anybody say yes? No, yes? No? Have the A's have it or have the nays have it? So, please. Have you seen parliament proceedings, the A's and the nays? Who are all saying yes for E equal to, small e equal to capital E? Who are all saying yes? No? Why are you so shy? And just think of me as your grandfather or something, and then you say whatever you feel like. Yeah. Yeah, tell me, doesn't matter. Don't be shy.
Mic ತಗೊಂಡು ಹೇಳಿ.
Different. Are you saying it different or the same?
It's greater than 3. It is different.
Different. Okay. No, the answer is they are the same. Small e equal to capital E. So two limits, but the two sequences, but the limit is the same. Okay. And that number, common number, is usually denoted by E, small e, not capital E, but small e. And as someone has already said, it is approximately 2.732, etc. Now you people have computers, had calculators, you can do it easily. You can take n very, let's say n up to 10, n equal to 10, let us say. The first one, you will get the formula 1 plus 1 over 10, 1 by 10 to the power 10. You calculate it. What is it? It is 11 by 10 to the power 10. A calculator will tell you what it is. If you're on your phone, if you have a calculator, kindly tell me what is 11 over 10 to the power of 10. I'll tell you why it is important that I'm asking you this question.
2.59.
2.59. Where is 2.59 and where is 2.73? 732 or whatever. You know that the approximate value is very close to 2.7, etc. So obviously, this way of approximating E, although it goes to E, this way of approximating E is not a good way of approximating E. It goes very slowly towards E, like an old man walking towards home. Whereas if you're a younger person, you walk very fast towards home. The rate is faster. So what I'm trying to say is, this comes in many studies like like uh, numerical analysis and so on. How fast does the 1 minute? How fast does does a sequence converge to the limit? There is a question called, which is very important in approximation. What is the rate at which it converges to a number? It is important, right? If you are trying this approximation or that approximation. Obviously, if you calculate using the other expression I gave you, you will find for 10 terms, you will get very quickly that it is much closer to 2.73, whatever. You can look it up. So that takes care of this mysterious number called E. And it is also called Euler's number. Euler, E-U-L-E-R, was a famous mathematician. Leonhard Euler, Leonhard, Leonhard Euler. And he posed this question. So Euler's number is important, okay? So now, let us move on to another question about this limit. Is E, do you know about rational, irrational numbers? What is a rational number? P divided by Q, where P and Q are whole numbers, right? That's what a rational number. We are only looking at positive numbers, so let's forget about negative numbers. P or Q must be positive integers. You divide one by the other, you get all rational numbers, all possible rational numbers. The question now is E rational or irrational? It's a very famous question, which bothered people for a long time. Okay. But it turned out that E is not rational. E is irrational. It cannot be written as P over Q. Right? You might have already seen the square root of 2 is not a rational number. You would have seen that proof. Or square root of 3 is not a rational number. But E is not rational is not such a easy thing to prove. Somewhat mysterious. It requires a little hard work. Okay? And you use this other expression that you have of 1 over 0 factorial plus 1 over 1 factorial up to 1 over n factorial, that sequence, En, capital En, you use that sequence to prove that it does not go to a rational number. Anyway, I won't go into proofs because, as I said, I'm not going into proofs here. Okay. It is 3:10, so I'll take another 15 minutes or so because we started so late. I had a teacher who would walk in late by 15 minutes and he would say, I apologize for starting the class 15 minutes late, but to compensate for coming late, I will let you off 15 minutes early. So, however, I am not like a teacher. I will take some extra time. Okay. Okay. So, let us now come to the question that somebody raised. Namely, if the terms in that series, if the nth term gets smaller and smaller, does it add up to something, the whole thing? Does it add up to something finite? Something which. So let us look at a very famous series called the harmonic series. 1 plus half plus 1/3 plus 1/4 all the way up to 1 over n. What is happening? 1 over n gets smaller and smaller as you get large. So does this whole thing 1 plus half plus 1/3 and so on, does it converge to anything? Does it go to some finite number? By the logic that you use, and also very many people who are just starting believe in, you're not the only one, that then it will converge to a finite number. But one knows that the sum does not converge to any number, and it grows larger and larger. So, do you have a board where I can stand up and and write a little bit? I can't stand for very long because of a back problem. Yeah, yeah. I'll hold it. I'll hold it. No problem. No. Oh, I can write like that. Okay. I can write with my finger. Thanks. Okay, so something else has come here. Oh. Can you all see?
Yes, sir.
So I'll write it as 1. Oops, not writing. 1. Right?
Yes,
It's 1.
pen.
No.
No, you have to dip the pen in the white color.
Previously you could write.
You dip the pen there, Sitaram. You dip the pen in the white color.
White color.
Oh, pen.
Yes, yes. ಬೇರೆ ಕಲರ್ ಆರೆಂಜ್
ವೈಟ್ ಅಂತ ಒಂದು
ಕೈ ಟಚ್ ಮಾಡ್ತಿರಲ್ಲ ಸರ್
Can I use my fingers?
Yes,
You
yes,
dip the pen
yes,
in the
you
white
can.
color.
Okay, then it's easier.
Oh, I see.
1. Okay. The second term is 1 over 1, no 0 here. Okay. Then plus 1 plus divided by 2 plus 1 over 3 plus 1 over 4 and so on. Right? Okay. But now I group them in the following way. Let us forget about the 1. We'll start with this. Half is half. Then we'll leave the 1 here. So 1 plus half. Then you look at 1/3 plus 1/4. Okay, that's greater than 2 times 1/4, right? Because you're getting smaller. So 2 times 1/4 is half. Okay, now you take plus 1/5, 1/6, 1/7 plus 1/8. This becomes, you group these 4 terms, and what does it become? 4 times 1/8, it's more than, that's greater than 4 times 1/8, right? So they're all getting smaller. 4 terms, and they're all bigger than 1/8, so it is bigger than 4 times 1/8. So that is half. So I would say all this is greater than half. The next you take would be from 9 to 16, right? 9 to 16, there are 8 terms, and that will be greater than 8 times 16. So that will be another half. Okay? So is that going to be finite? Each term you are adding a half, which is not going down to 0. So after such n steps, I'll say k steps, where k is equal to 2 to the power n somewhere. 2, 2 squared, 2 cubed, 2 to the 4, and so on. K steps. After 2 to the n steps, you will get n over 2. Add it all, n over 2. So it blows up, right? As n gets larger, it blows up. So here is an example where the individual terms are getting smaller and smaller, but still the thing blows up. Okay. And many of you have probably done integration. I will show you another way of doing it, which will tie it up with integration. It's always interesting to connect the two different concepts together. So let us see. So you would have heard the word that integration is nothing but a way of summing things, adding things, to integrate things. Okay. So how do I erase this? Erase, undo. Erase. Okay, now once again. Okay, I'm right. Yeah. So let us, this is a graph. Everything is positive, so I don't have to worry. So I come to 1. I consider the function f of x is, f of x equal to 1 over x. So I consider this function. It will go down like this, right? As x gets larger and larger, it gets smaller and smaller. So this difference will go to 0. What do you call it? That height you call some name, right? One is ordinate, the other is something. Abscissa and ordinate, or ordinate and abscissa, I don't know, remember. Anyway, the concept is more important. So at 1 it is 1. At 2 it is half. It's not drawn to scale. Okay. Half. 1. 3 it is 1/3. And so on. So what are you doing in summing up? This is all unit length. So look at this triangle. You are looking at the area of this triangle, not triangle, rectangle. I mean. Rectangle. This rectangle has area how much? 1, right? Height 1, width 1. So what is the area of the next rectangle? Half. This is very nice, writing it with your fingers and all. I like it. Maybe I should buy one such board. I don't know. Is it very expensive?
No.
No? No, maybe it costs a lakh of rupees or something. I can't afford that. But it's really fun. Then 1/3 to 1. This becomes 3, 4. Width is still 1, but this is 1/4, right? 1/3. So this area is 1/3. And do this, keep on doing this, you will get 1/4. This is 5, this outer area is 1/4. Correct? Now, what is the area under the curve? Up to, let's say we stop at some point, it is the integral of 1 to n over 1 over x. Either n or n plus 1, I don't know, n I suppose, right? N. Huh? Right, up to n if you stop. That will give you up to 1 plus half plus 1/3 all the way up to plus 1 over n. Okay. This thing is known by the grand name of integral test, but it's nothing, it's simple, it's elementary. Okay. So what do you get? Huh? Integral is, I'm doing log to the base e, right? You're all familiar with that. I get log n, right? The antiderivative of 1 over x is log x. You are doing it from 1 to n. At 1 it is 0. At n it is log n. So this sum is greater than or equal to dot 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 is greater than or equal to log n. What happens to log n as n gets larger and larger? Forget about base e. Let's look at base 10. Just to give you an idea. What is log of 10? It's 1. Log of 100 is 2. Log of 1000 is 3. And so on. So log n also blows up. Maybe not as fast as n, but it blows up. So what does it say? It tells the area under the curve is bigger than or equal to, under the curve up to n is bigger than or that sum is bigger than or equal to log n, and log n itself is blowing up. Therefore, that sum has to blow up. So this is a simple proof. If you want, this is a geometric way of visualizing why 1 plus half plus 1/3 is greater than, is not, is the word used is divergent. See, in mathematics, we shouldn't be frightened of lingo. You can easily master lingo. It's the concepts that are difficult to master. Not difficult, but more difficult to master. So, as I said, it's very simple. This whole thing is very simple. Supposing you apply the same logic, what is this? Erase something. Erase. Yeah, this is great fun. I think I will offer to give more lectures just to play around with this board. If you allow me to play with this board, I can lecture every day. Okay, so this thing, let us do this series. 1 plus half squared, 1 over 1 squared plus 1 over 3 squared. So this is the squares of the natural numbers. Okay. 4 squared and so on. The general term will be plus 1 over n squared plus. Okay. Similar to what we looked at. Nth term is getting smaller and smaller, 1 over n squared, but is going to 0 more rapidly than 1 over n. But so what? Does it go to Does it go to zero? Does it, I'm sorry, it goes to zero, but is the sum approach a finite sum or it doesn't? Take a guess, doesn't matter. Take a wild guess. Let's say this is a quiz and I ask you who acted in such and such a film. If you don't know, you will just take a guess, right? So no negative marks for taking a guess. So anyway, take a guess. Not convergent. It will blow up, you are saying. The sun up. Do you know what pi is? Ratio of the circumference to the diameter, right? That number is called pi. And as we all know from high school, that it is approximately 22 over 7. Very approximate. Not very reasonable approximation is 22 over 7. That's also another irrational number. So we don't have an exact formula, but it's approximately 22 over 7. So this sum of the series turns out to be, that is, if you take larger and larger partial sums. They are called partial sums for obvious reasons. You will get pi squared divided by 6. Very famous formula. Sigma 1 over n squared, as they say, sigma 1 over n squared, n equal to 1 to infinity. It's a way of writing is equal to pi squared over 6. One of the very famous formulae in the old days. This was posed also by Euler, actually. This problem, give me a sum. See, I hope that in the third lecture I will do something called Fourier series. And using Fourier series, I can prove this for you. We can prove it is what is called convergent, that it will go to some sum by the pictures that I drew using such picture. But you cannot find what that sum is by using those pictures. But with a little more work, little more knowledge, we can show that it is pi squared over 6. So I'm tired now, so good time. You are also probably tired of hearing my voice, so you should also take a break, and then Professor B.V. Rao will take over from me. What do we do? Give it to you. May I make one small correction? My name is Alladi, and the second name is, you have blessed me with a few extra letters. I'm very grateful for that. But my name is Sitaram. That's it. Sitaram. No An and not W-E-T-H. Just Sitaram. Why my name has been spelled like this, you have to ask my father and mother. That is the way. No A. I come from both Andhra and Tamil Nadu. In Andhra, the AN is not used, so I'm bilingual. Sorry, I shouldn't say these things, but I thought it's worth pointing out. Okay, I enjoyed that hugely. It's good that I met you and explained this to you. And we are going to take a break right now. And, yeah.
Thank you so much, sir.
Thank you. Any questions about it? Anybody?
Any questions?
Do you have any questions?
Shall we?
Yes. Now I call upon B.V. Rao sir to
So we'll have a break for 10 minutes. Students, leave your bags here only and you can come back after 10 minutes. We'll continue with the talk later.
Please be here.
you.
ಸೀಟ್ ರಿಸರ್ವ್ ಮಾಡಿ ಹೋಗಿಮ್ಮ.
ಯಾರು ಇಲ್ಲ ಸ್ಟ್ರೀಮಲ್ಲಿ ಇರ್ಬೇಕಾ ಬೇಡವಾ ಮ್ಯಾಮ್.
Okay, and I
Professor B.D. Rao sir.
Thank you. Mic is here? Okay. All right. So let us see. If I am shouting too much, we will remove the mic. Okay. All right. Is it on? Okay. You can put in pockets. Yeah. Okay. So we are going to discuss probability. But before I start, do you have any questions? Because the most important thing is to answer any questions you might have. Okay. Okay. Some of you have probability in your school and so on and so forth. We will start from there. Okay. So first of all, why are we doing probability? What is probability? Any idea
Measuring chances.
about it?
It is about measuring chances of occurrence or not.
Okay, but basically, probability is the analysis of experiments which depend on chance. Okay, so just as physics is analysis of experiments which are deterministic. Okay, you throw a chart from here, then if you know initial position and velocity, you can tell how it is going to travel. But that is not entirely right. Why? Because it assumes that there is no other force acting, okay, except gravity. But most of the time, we have a fan in the classroom. Of course, this is probably, as you know, we don't have a fan. There is fan. Okay. Then fan, wind from the fan will disturb this. Okay. So the thing that you learn, and how does it disturb? You cannot write down, okay, the force exerted by the fan wind. It is random. You yourself can feel when you sit under a fan, sometimes heavy wind, sometimes less, right? So it is random. So experiments that depend on chance, okay, is essentially this. So the so-called you read in newspapers AI is all random experiments. Machine learning, random experiments. Okay, and in physics, you will hear about several things like percolation and so on, random experiment. Okay, you can't tell. If I put a water drop here, okay, slowly it spreads. You can't tell how it spreads. Okay, there are several things acting on it, random. Okay. So similarly, magnetism, random. So everything that you observe in practice, okay, even though we have deterministic theories, there is always randomness added to that. Okay, so analysis of random experiments is chance. Of course, in olden days, when science was not so much developed, the only randomness that came is through gambling. Okay, so you play card game or some such thing. That is randomness. Okay, you don't know what happens. Okay, so people sort of identify probability with gambling. Okay, but slowly, when we discovered the power of probability, we started using it all over. Okay, and AI is essentially probability, nothing more than that. So let me start with simple things that you have learned in high school. Suppose I have got, let us say, 5 balls, okay, numbered 1, 2, 3, 4, 2, 3, 4, 4, 5. I have 5 balls, okay, and I want to put the 5 balls in 3 boxes, A, B, C. The balls are numbered, ball number 1, ball number 2, okay. This is the experiment. I want to put them at random. So what is this at random? Okay, as you learned in school, first of all, whenever you have an experiment, the collection of all possible things that can happen, is called sample space of the experiment. Okay? Imagine yourself distributing the 5 balls into the 3 boxes. Okay? For example, ball number 1 may go here, 2, 3 may go there, 4, 5 may go there. Or 1, 2, 3, 4, 5 may go here, nothing there, nothing there. Right? There are many possibilities. So the collection of all things that can happen is called sample space. And the total number in the sample space is counted. And if you ask any question, we calculate the probability of something happening as the number of ways that happens divided by total number of ways. That is what we do. For example, in this, how many outcomes are there? 5 to the power of 3 to the power of 5. Why? Because, well, permutations and combinations. Most of the time in high school, we solve permutation and combination problems. And then we look at the answer. If the answer is wrong, we try to correct it. Okay? That is the end of it. But however, you don't have to look at the answer. Whenever there is such a question, you pretend you are doing the experiment. Okay? Pretend that there are 5 balls in your hand. First ball, ball number 1, you can put in any of the three ways. Ball number 2, you can put in 3 ways. Okay? Ball number 5 in 3 ways. Therefore, the total is 3 into 3. 3, 4, 5. Okay? Now, suppose I want to ask, what is the probability that there are 2 in A and 3 in B? Let us see, 1 in, how many are there? 0. 0 in, I want. So, first of all, do you understand what is the experiment? Most of the time when we read a problem, we are very eager to solve the problem rather than understanding the problem. Only when the answer is incorrect, we go back and read the problem. Okay, you don't have to be that fast. Okay, you can try to understand what is happening. So this is the experiment, and the total number of outcomes is 3 to the power of 5. Now, I want to know what are the chances that there are 2 balls in box A, 3 balls in box B, nothing in box C. So I have to see how many such outcomes are there. Okay, let us see. Suppose I ask you to put 2 balls in box A, 3 balls in box B. What would you do? Among the 5, you pick 2, put them in A, and the other 3 you put. That's it. Nothing in C. Okay? Therefore, the total number of ways is simply 5 choose 2. That's all. That is the total number of ways. After you select 2 balls, put them in A, there is nothing for you to do. You have to put the remaining 3 balls in B, that's it. So you don't have to count anything. So the probability is this divided by 3 to the power of 5. Suppose I want to know the probability 1 in A, maybe I should say 2. 1 in B and 2 in C. Okay? What is the probability that there are 2 balls in A, 1 in B, 2 in C? There is nothing for you to think. Exactly the same philosophy. Pretend that you are doing it. Don't try to guess. You don't have to guess ever. Okay? Pretend that you are trying to put the 5 balls in the boxes so that this happens. What would you do? You will pick 2 balls, put them in A. Then you will pick 1 ball, put them in B. Other balls you put them in C. Therefore, here this is 5 choose 2, and then there are how many remaining? 3 choose 1. Okay, you can simplify that. Okay, I don't have to take it that way. I can write the answer. Okay, you don't have to do anything more because the remaining 2 will go in C. This divided by 3 power 5. This is the answer. Okay, so that is how we do probability. You can calculate probability of an event and the number of outcomes possible in that event divided by total number. This is because we are assuming all outcomes are equally likely. Sometimes they may not be equally likely. Okay. For example, Suppose you are manager of a company which is manufacturing boards. A board has certain specifications. The board may be good, may be defective. Okay, can you assume that they are equally likely? If they are equally likely, you should come out of the company. Okay, the chance of defective board should be very small, not equally. But why are we doing equally likely? Because whenever you develop a theory, start with simple cases. Then try to do complicated cases. That is why we start with this. Okay. Now I will ask you another question. I have 5 balls. Again, exactly like that. I have 3 boxes. A, B, C, exactly like that. Okay. What is the difference? I have written 1, 2, 3, 4, 5 here. I have not written there. They all look alike. Okay. Think of them as tennis balls from the same company or cricket balls from the same company. They all look alike. Now I will ask you, in how many, so I am going to put the balls in the boxes again. Same problem. How many outcomes are there? Okay. So, can you argue like this? You cannot. Why? Because here, what did we do? 2 balls in A, 1 in B, 2 in C. We said pick any 2, put in A, and then pick any 1, put here. That doesn't work out here. Why? Because if you put these 2 here, that is same as putting these 2. I can't find out. Okay? All the balls are looking alike. You understand the problem? All the balls are looking alike, and I want to find out the number of ways in which you can distribute these balls in the boxes. Right? And outcomes are different if your eye can distinguish. Otherwise, they are not different. Okay? Putting, again, let me repeat. Putting these 2 balls here, these 3 balls here, okay, is same as putting these 2 balls here and these 3 balls here. Same. But I thought this will be done looking alike. Okay? Therefore, that counting, namely 3 to the power of 5, is no longer true. You understand? How many outcomes are there? Now, I want to know. How shall we solve this problem? There are several ways of solving this problem. Okay? There are several ways of solving this problem. You see, an outcome is determined by the number of balls here, here, here. That's all. Nobody is going to ask which ball is in A, which ball is in B. So every outcome is determined by 3 numbers. Balls in A, balls in B, balls in C. That's all. So as soon as you tell me 3 numbers A, B, C, non-negative integers adding to 5 and so on, that gives you a way. And every way of putting is given by those 3 numbers. Therefore, you have to tell me the possible triples ABC, non-negative integers, they could be 0, so that they add to 5. Okay? How do we find it? Well, as I said, there are several ways, but I will tell you one interesting method, which is very quick. What I do is the following thing. I will draw 7 cross marks. Okay? There are 7 cross marks here. I want to make the following statement. If I select 2 cross marks out of these 7, make them into vertical lines, then you will get a way of distributing the balls. Conversely, every method of distributing the balls can be obtained by my procedure. Okay? So you understand, I said, if you select two of these cross marks, make them vertical lines. Suppose I make this vertical line and this vertical line. How many crosses are remaining? 5. Do you feel that gives you how to put the box? Yes. 2. This is the first box. A. This is the box B. This is the box C. So put 2 in box A, 2 in box B, 1 in C. Okay. So if I select 2 crossbars, make them into vertical lines, that gives you a way of distributing. Now, let me give you another example. Okay. You might say, I will select this and make. I will. You can say that. Don't worry. Even then, you see 3 boxes there. Below the first line, 1 box. Between the 2 lines is the second box. After the second line, the third box. That's all. As here. As here. Okay? You may get worried. You may get confused. If you don't do that, if you think this is same as this kind of thing. Okay? So what is this telling you? Put nothing in A. Put 5 in B. Nothing in C. That's all. Okay? Therefore, every method of selecting 2 of these cross marks, making them into vertical lines, will show you 3 boxes. 1 box before the first vertical line, box B between the 2 vertical lines, box C after the second vertical line. Okay. And conversely, if you tell me I am going to put these balls, this number of balls here, this here, I can show you how to get it from here, obviously. Okay. If you want to put 1, 3, for example, then I will select this, make a vertical line, 1. So on. You can quickly. Therefore, the number of ways of distributing the balls is same as the number of ways of selecting 2 of the cross marks. Okay, make them into vertical lines. That's it. Therefore, that is 7 choose 2. 7 choose 2. Okay. Now, suppose you ask, what is the probability that 2 are in A, 3 in B, 0 in C? There is only one way. Because earlier there were so many ways. Why? Because the balls are numbered. Now, the question, which ball went into A, makes no sense. As long as 2 balls are here, that's it. There is only one way of putting that. Therefore, probability of this is 1 by 7 choose 2. Similarly, probability of this is 1 by 7 choose 2. Okay? There is only one way of distributing 2 in A, 1 in B, 2 in C. You see the point? Because balls are looking alike. Okay. Now comes the question. Why are you wasting our time by putting the balls into boxes and answering this command? By saying that boxes are distinguishable, the balls are looking alike. Okay? Have you heard of S.N. Bose? Have you heard of Einstein? Yes. This is called Bose-Einstein experiment. This is the Bose-Einstein experiment. Okay? And what have Bose-Einstein got to do? How come suddenly talking about balls and boxes, we make some nonsense there, Bose and Einstein? In probability, we say toss a coin, throw a ball. This is all ideal. This is all a symbol. Ball need not be balls. Boxes need not be boxes. Imagine for a minute that the 5 balls are 5 photons coming into this room. Imagine the 3 boxes are the 3 energy levels. This is one energy level, that is another energy level, that is another energy level. The 5 photons are occupying three energy levels. Okay. In how many ways can they occupy? It so happens that was the great discovery of Bose, S.N. Bose. Photons behave like identical particles. Okay? Identical particles. They all look alike. Therefore, the number of ways these five photons can occupy these three energy levels is this. Okay? And if you ask any question, what are the chances that the photons occupy in a particular fashion? It is 1 by this number, 727. These are called Bose-Einstein statistics. Okay? And when quantum mechanics was developing, Planck has certain calculations and so on, but however, people were not able to explain. Okay? Bose came out with this explanation. Okay? And this is an outrageous explanation. Nobody accepted that in the beginning. I will tell you why this is outrageous. Suppose I have a box. Okay? Suppose I have 30 red balls and one green ball. What is the I select a ball at random. What is the probability of selecting a green ball? 1 by 31, isn't it? Because total number of balls is 31. Only one green ball. Probability is 1 by 31. Suppose I told you all the red balls look alike. All the green balls, only one green ball is there. Okay, all the red balls look alike. Then, can you say that there are only two outcomes, red, green? No. No. In other words, this Bose explanation does not apply here. Okay? This experiment does not follow the Bose mechanism. Whether the balls are distinguishable or not, if you have put 30 identical red balls, one green ball, the chance of a green ball is 1 by 31. You cannot say it is half. You cannot say you will apply Bose philosophy. That is why it is outrageous. Okay? It doesn't apply here, but it applies there. Of course, you might ask me, why would it apply there? Nobody knows. It is only photons who know. Okay? Because they follow that. We can't help it. Right? Okay. So, this is an analysis of one experiment. Okay? Let me see. How do I erase this?
Single click, sir. One. Slide.
Okay. Palm eraser. Oh, I have to do this? Okay. Oh, yes, there. Okay, fine. Thank you, thank you. Okay. So, in a simple experiment, if you slightly change, that is why mathematics is like music. There is a basic structure. Okay. You slightly change the basic structure, you will get another raga. Okay? You see, that's the whole thing. Alright. Now, let me go to another interesting concept in probability. That is the following. Suppose I have, let us say, 20 red balloons and 30 red balls, and let us say 40 blue balloons and 50, let us say, blue balls. Okay, I have a box. There are 20 red balloons, 30 red balls, 40 blue balloons, and 50 blue balls. By the way, in the earlier experiment, I have taken 5 balls and 3 boxes. But in practice, you take, okay, R balls, N boxes. Alright? Because there are large number of photons and so on. However, whenever you read, this is something you should remember. Don't remember by rote. N plus R minus 1, 2 R minus 1, nonsense. Try to see for 4 and 5 what happens. 5 and 6. You will get the general formula yourself. You don't have to look at the book. Okay. Alright. Now I pick one at random. Okay. What is the probability that it is red? I will ask the question. So, I pick one. How many are there? 5, 9, 140. Yeah, 140 items are there. I pick one at random. What is the probability that the thing picked is red? Okay, there are 20 red balloons, 30 red balls, so 50 red things are there. Total is, I forgot what it is, 50 by 1 part. Is it okay? You all agree? Yes. Now comes interesting. Probability, I said, is analyzing experiments where some uncertainty is there. But many times our ignorance is partial. Okay? We know some information. We don't know some information. For example, will it rain this evening? Okay? You don't sit down and say half and half. Okay? The weatherman will look at the cloud concentration, the wind speed, the temperature, the pressure. He has information of all that. So his question is, given all that information, will it rain in the evening? That is the question. Okay? That is the question. Therefore, probability analyzes experiments where you don't know anything or where you know something and you don't know some things. So here, I know that it is a balloon. What is the probability it is red? Okay. I picked something at random. I told you it is a balloon. Okay? Information is given. So whenever you see such a thing, given after the vertical line is the information given to you. That is true. Given that information, what are the chances that it is red? Of course, you can still be stubborn and say, I don't care what information you give, it is still 50 by 140. You are free to say that. But that is useless. Okay? That is useless. So, to be practically useful, you should take this information into account. How do you do that? How many balloons are there? 60 balloons are there. Of them, how many are red? 20. So, this is 20 by 60. This is called conditional probability. Okay? And one smart fellow made a beautiful observation. This is same as probability of red balloon, red and balloon, let me say, divided by probability of balloon. What is the probability? It is red and balloon 20 by 140. Look at that. Ignore this thing for a minute. Okay? Look at this. So what is the probability that the item is red and balloon? It is 20 by 140. What is the probability it is balloon? 60 by 140. Therefore, this is 20 by 140, this is 60 by 140, that is same as that. Okay? What is the advantage of this smart observation? The conditional probability can be defined using probabilities. Okay? So, now, so far I am avoiding symbols. Okay? I will. Probability of A given B is equal to probability of A and B divided by probability of A. This is the conditional probability definition. Now, what is A, what is B? You see, I gave you example written below, but you don't have to think of this example, okay? Take any experiment. We are thinking of experiments with finitely many outcomes, don't worry. Okay. And take any event. What is an event? A set of outcomes. Okay. So A is a set of outcomes. B is a set of outcomes. I ask you what is the chances of A, you will say number of outcomes in A by total number of outcomes. If I ask you what are the chances of A given B, then the definition is it is probability of A and B, that is outcomes common to both AB divided by total number of B, number of outcomes in B. I have written it as probability of A and B by probability of B by following this. So again, I don't know whether in school they do conditional probability. Do they do? They don't do. Yeah. Okay. Anything that is interesting and useful, we don't do in school. Anything that is boring, we quickly do it, so that the students will never learn. Okay. They hate the subject. Okay. So this is the concept of conditional probability. And conditional probability can be used whenever you have a mathematical equation. A is equal to B by C. If you know BC, you can calculate A. If you know AC, you can calculate B. Okay? Therefore, probability of A and B is probability of B into probability of A given B. You can do that. Okay? So this can be used in several ways. I will tell you one interesting thing. Okay. I have 15 red balls. We'll play a game now. This is a game which can be played forever. Okay? So what I do is the following. I have 15 red balls and 20 black balls in a box. And I have lots of balls with me, don't worry. Pick one at random. See color. Put it back. Okay? Add one ball of that color. Okay? There are 15 red balls and 20 black balls here in the box. I pick one. I see the color, put it back. I put one more ball of that color. Now the number of balls is 36. You can do it again. There are 36 balls. Pick one, see the color, put it back. Add one bar of that color. There are 37. Do it again. If you are not tired, you can do it forever. Okay? This is a beautiful game. We will ask some interesting questions and try to answer them. Okay? So, for example, what is the probability R1? By the way, when I say R1, red in the first draft. Okay? Suffix. Because we are doing the experiment forever, isn't it now? So, when I say probability of red, it's a meaningless thing. Red one in my first attempt or in my second. When is it? So R1, probability of red. What is it? It is 15 by 35, isn't it? 15 by 35. I want to know what is probability of R2. 16 by 36. 16 by 36. 16 by 36. Why? Who said I added one more bar? Where? Did I ever say I added a bar? Red bar? I never said. I only asked this question. I never said what I added. If I said I added, you are right. I never said. Okay? This is another thing you should learn. Sometimes to make some calculations, you need some information, just as you needed what I added. Such informations are missing. But who asked you not to bring in that information? Bring it. Whatever information is lacking, bring it. Okay? So how do you bring it? This event I can write in union of two sub-event R2, R1, R2, B1. I am writing in symbols. What is this event? Second ball is red, first ball is red. This is the second ball is red, first ball is black. This event consists of these two sub-events. Is there anything that can happen? No. Second ball is red. I am interested in that event. That event consists of two sub-events. Okay? First red and second red. First black and second red. Okay, what is the probability of this? Probability of this, as I said, you can use a formula in several ways. This is R2 and R1. You already told me probability of R2 given R1, isn't it? You said that is 16 by 36, right? Therefore, you can use this formula. Probability of this is nothing but probability of R1. What is that? 15 by 35. Did I get that? 15 by 35. 15 by 35 into probability of this given this 16 by 36. Huh? Wait a minute. What is happening? 16 by 30. Do you agree that probability of this is this? Okay. Here we know conditional probabilities. We know the conditional probability R2 given first is red. I don't know what is probability of R2. Okay. Therefore, we use that. The information that is lacking is what was the first one. You should not hesitate. Any information that is lacking, bring it in. Okay. This is plus. These two events are disjoint. You all agree. For two disjoint events, probability of this union, this is some of the probability that is very easy. What is the probability of this? Probability of B1. What is probability of B1? 20 by 35. First ball is black, is 20 by 35. Second ball is red, given the first is black. It is 15 by 36. Correct? Probability of B1 into probability of R2 given B1. What is that sum? Okay? Don't brutally multiply. Okay? You can take 20 by 35 common. No, 15 by 35. 15 by 35. 15 by 35. There is 15 by 35 in both. Take the common. Don't multiply anything. You see? Sometimes you have to pretend that you are lazy. Okay? Don't multiply. If you take it out common, what is there? 16 by 36 plus 20 by 36. What is that? Therefore, it is again 15 by 35. Okay? Similarly, the chance of red ball in the third graph is also 15 by 35. You can show that everything is there. But there is something changing. Okay? What is changing? Probability of R2 given R1 is strictly bigger than probability of R1. Why? This is 15 by 35. What is this? 16 by 36. This is 16 by 36, you already said. 16 by 36 is bigger than 15 by 35. Okay? We will not spend time. You can easily verify that. Okay? Cross multiply, nothing profound. Okay. Therefore, if you see a red ball, chances of red ball is increased. Okay? If you see a red ball, chances of red ball is increased. However, chances of red ball is same all the time. Okay? It is only the conditional chances that are increased. Okay? This is a beautiful game you can play. Why are you wasting our time? Why are you playing with these math nonsense? Come on. But what you don't realize is this is something you see in practice. Is there anybody here who is not from Bangalore? All of you are from, you are not from Bangalore. Where are you from? Huh? Oh, Kolar. Okay, very good. So, our friend came from Kolar. Okay. Before she started in Kolar, somebody told her, be careful. There is a lot of flu in Bangalore. Be careful. Okay. Maybe 1% of people have flu or 0.1% have flu. So the chances of seeing a person with flu is okay, very small. 1 by 100 or point. Isn't it? Always same. But consider our friend who comes from Kolar. She comes to Bangalore. She sees a person with flu. Oh my God. I was told in Kolar there's a lot of flu. I have met this fellow, he has a flu. There must be a lot of flu here. Isn't it? Suppose she walks and finds another person with flu. What does she think? Oh my God, oh my God. Why did I come here? Okay. There's a lot of flu here. It's her experience makes her think there is a lot of flu here. But whatever her experience is has nothing to do. There is some percentage of the population who have flu. That's all. Okay? Therefore, you keep on changing your ideas depending on your experiences. That is what is happening here. Red ball is an indication of flu. Black ball is an indication of not flu. If you saw a person with flu, you will increase in your mind that there is a lot of flu here. Okay? That is what this is showing me. Alright? So this is a very beautiful thing. And now let us see. We will go to something else. By the way, again,
Shall I do, sir?
well,
Eraser.
yeah, you can do it. There is a lot of interesting thing here. Okay, so thank you. Remember, mathematics is like music. Okay, when the basic idea is given, you should not accept completely. You should try to think on your own. You should always question whoever it is, your teacher, etc. Okay? Of course, don't question the government outside this college, they will put you in jail. But as far as mathematics is concerned, you should keep on questioning. You can question, why did you add one bar? Why not 10 bars? You can add 10 bars. Same thing remains correct. Same thing remains correct. Probability of red is still same. Okay. But what has that number 10 got to do? If you saw red ball, probability is 15 by 35. Suppose I added 10 red balls. Then what is the probability of seeing the red ball? 25 by 45. Right? That is much more, much more than 16 by 36. Therefore, 10 will tell you how nervous you are. Okay? So, if our friend is very nervous, okay, terribly nervous person, when she sees one fellow with blue, she might even leave Bangalore. Okay? She will assign high probability for seeing people with blue. So that 10. Why don't you add a ball of that color? Why don't you add ball of opposite color? You can do that. Okay? That is also useful. Why? Because there are safety measures on the road. There are police, law enforcement people. What do the police do? They sleep. Okay? When accidents are increasing, then what do? They keep on putting safety measures one after the other. Then accidents will fall down. Then they sleep. What happens? Accidents will increase. Then they wake up. Okay? So safety measures and accidents. As the accidents increase, you put safety measures. As the safety measures increase to reduce the accidents, then these things come down. You don't want it. So that is also nice thing. You can add a ball of that color. Okay? And you can say you can give thought to your imagination, you see. Why should I add only this or that? Why don't I add two red bars and three black bars and so on? You can do everything. Lot of research goes on in that by the way. Okay, so that is one important thing. And now I will tell you another thing. This is the concept of independence. Probability of A given B is probability of A intersection B by probability of B. Okay. Therefore, if I want to say that the events A and B are independent, this is another concept. I don't know in school this is done or not. Generally, they do. They will ask you to multiply the probabilities and so on. Okay. All right. So the two events A and B are independent if they have nothing to do with each other. Like, what is meant by nothing to do with each other? Even if I told you that B happened, probability of A remains the same. Therefore, two events A and B are independent if probability of A given B is same as probability of A. The fact that you told me B occurred does not influence A. What is meant by saying probability of A given B is same as probability of A? Probability of A is equal to this. That means P of A intersection B is P of A into probability. Okay? Two events are independent if probability that they happen together is product of the probability. Okay? And the reason we make that definition is because we feel that the events are independent if the probability of A does not change even if you tell me B occurred. That's why. That is why this is. Okay? Now let us look at one interesting thing. Similarly, 10 events are independent. Probability of that happening all the time simultaneously is product of the probabilities. Okay. Alright. Let us look at an experiment. Okay. Probability lives on experiments. We keep on doing experiments. I have a coin. Okay. Whose chance of heads is 0 is less than 3, less than 1. Okay. Plain coin means chance of heads half. Okay. It may so happen that chance of heads is 1/3. But yeah. Okay. For example, I might roll a die. On 2 faces, I will write 8. On 4 faces, I will write 8. Chance of seeing H is 1/3, isn't it? So it's 2 by 6. That can happen. Now, I toss the coin independently, let us say 5 times. Okay? Now, here you should carefully understand what is meant by toss independently. Does it mean I toss once, go out and have a coffee and come back and toss again? Nobody cares what you do. Do whatever you want. What are important are probabilities. What probabilities will you do? Okay, that is the most important thing. It doesn't matter what to do. Okay, you may sit in the chair and talk, then stand, talk. So independent means the result of first toss, the result of second toss, etc. They are independent. Okay, that is what it means. That is the technical meaning. Now, let us try to understand this experiment. Okay, what are the outcomes first of all? If you toss a, you see, you don't need mathematics. If you want to understand the outcomes of an experiment, pretend that you are doing the experiment, that's all. What can happen? So, if you are doing this experiment, the outcomes are sequences of H and T. I have written one sequence. That's an outcome of this experiment. First toss is heads, second is tails, third, fourth. Or all heads, or all tails. How many outcomes are there? 2 to the power. Okay? Because the first letter could be HRT, second HRT. There are 2 to the power of outcomes. What is the probability of each outcome? Now they are not equally likely. Okay, we have sort of graduated from elementary school to high school. Okay, in the elementary school, all outcomes are equally likely. Probability of calculating an event is simply counting how many outcomes are here, total number of outcomes, and so on. But now we have graduated to a little higher level, little complicated experiment, and but we can associate probability for each outcome. What is the probability of this outcome? Probability of first class head multiplied by this and so on because of this relation. Okay, I am tossing the coin independently. That is what it means. I said tossing the coin independently does not mean you toss once, go out and have a coffee, come back and toss again. Okay, the word independently is dictating to you how to assign probabilities. That's more important. Okay, so probability of this outcome is p to the power of 4 into 1 minus p into 1 minus p into p into p into p. What is this outcome? First class is head, and second is tails, and third is head, and fourth is head, and fifth is head. Probability is product of the probabilities. Okay? There are 2 to the power of 5 outcomes, and we are supposed to be intelligent people. We don't want to write all the 2 to the power of 5 outcomes on the board 32. We can write and write down probability of each. We don't want to do that. Without doing that, we want to calculate probabilities of certain events. What is the probability of exactly 2 heads? I want to know that. Again, what is the probability of an event? When all the outcomes are equally likely, we counted the number of outcomes in the event by total number of outcomes. Now, outcomes are not equally likely. Therefore, we use alternative definition which is equivalent to that. Look at your event, see what are all the outcomes there, look at the probabilities, add them up. Okay? Earlier, if all the outcomes are equally likely, let us say 100 outcomes. Suppose your event has 20 outcomes. Then each outcome has probability 1 by 100. Therefore, you adding 1 by 100 20 times is same as etc. We did the same thing there also. But now we do exactly the same thing, which means to calculate probability of an event, you have to look at what are all the outcomes in your event. You see what is the probability of each, add them up. Okay. Now, exactly 2 heads. Luckily for us, we are saved because no matter which outcome you take, with exactly 2 heads, it has this probability. Take any outcome with 2 heads. Okay, this is an outcome with 2 heads, isn't it? Probability of that is this. Suppose I look at this one. That is also 2 heads. This probability is also this. Luckily for us, all outcomes where exactly 2 heads appear have the same probability. Therefore, we shall be adding the same number as many times as there are such outcomes. Remember, probability of the event is add probabilities of all outcomes. If all outcomes have the same value for their probability, then you are adding the same number so many times. Therefore, you have to count how many outcomes are there. That's very easy. There are 5 possible places for heads and tails, in which there should be head exactly 2 times. Take any 2 places among the 5, put heads there and others put tails there. Therefore, I choose. So this probability is equal to this. Okay? Now you can see what is the probability of 3 heads. 5 choose 3. PQ into 1 minus P whole square. Okay? No. If the outcomes are equally likely, that is, if the coin is paired, heads and tails have the same probability, this is half. This is also half. It will be half power 5. That's all. Okay? Therefore, this is called binomial probabilities. Why binomial? You can see that. Okay. What are the probability of 0 heads? 1 minus p whole cube. What is the probability of 1 head? 5 times p times 1. So these are the successive terms in the expansion of 1 minus p plus p whole power 5. That is 1 power 5. Okay? Therefore, these are called binomial probabilities. Right? Okay. Now, I will just tell you one more thing. And when should I stop? No, when should I stop?
No, now only, sir.
No, only? Yeah.
No, no.
Oh, good. Oh,
You
good.
can wait.
So, what I do is, by the way, have you ever come across binomial probabilities? Okay. Poisson probabilities? Oh, Poisson also. Okay, fine. So, very good. So, next time, I will describe Poisson probabilities. Okay. And then, we shall go to another interesting thing using these things. Okay. And where you have to do lots of calculations. And then we shall go to random walks. Okay. And also in the third lecture, I shall explain some things which are more general than random walks and how those things will occur in AI and machine learning and everywhere. Okay. Okay. Thank you all. By the way, if you have any questions, so please shout. Okay. It is your fundamental right to shout. Okay. Whenever you listen to something. Yeah.
Any questions? ಅಲ್ಲೇ ಇದೆಯಲ್ಲ.
But oh, that's okay.
Sir, you can.
Anyone have to ask the question?
Any questions or any doubts? Sir,
Hello.
sir, we'll give mic, sir.
Yeah, yeah.
Maybe you can tell them
Photo.
maybe you can tell them about the, about the, about vaccination and false tests.
Oh, yeah.
False. That is also
There is
involving
something
such.
called
Yeah.
Bailey's and so on and so forth, which is related to conditional probabilities. That's a very important technique in probability. It's called Bayes' part. Many times, conditional probabilities, there is a peculiarity. Probability of A given B, probability of B given A. Okay? So, the chances in the first, suppose you go to the doctor. I will say, oh my God, I have cancer, I have cancer.
Sir,
What does the
mic,
doctor do? He will say, get the test done. Okay? No, that's unnecessary. I'm shouting loud enough for this room. So he will say, get the test done. And the test
You
will say, positive. I have. So what is the thing here? Test said, I have cancer. But do I have cancer? He has to decide. Okay? So given the test said that I have cancer, do I have cancer? We know the other kind of probability. Whether the test says yes or no, if I have cancer, it depends on your laboratory precision. By looking at the machine precision or the laboratory fellow's laziness and so on, you can decide what are the chances of you saying I have cancer if I have cancer, saying that I have no cancer even if I have cancer. Those things you know, but you know the opposite probability. They also are very useful.
You can. Nice, sir.
Once again, thank you for your precious time, sir.
So try to think